Let me take away these notes. We are here to learn chemistry. And if you remember where we left off, the life of Gaffney, teaching chemistry from his porch, we have left off discussing electron orbitals and energy levels. Electron orbitals and energy levels. So, we've discussed the idea that electron orbitals are things that are surrounding the nucleus of an atom, and around the nucleus are these vaguely defined places where electrons hang out. And we've talked about different types. We talked about 1, 2, 3, 4, and so on. So there's some rules to these orbitals. First of all, we have the energy level, the energy shell. The shell. The shell is a set of orbitals. A set of orbitals having the same n value. Okay, just want to make sure I'm all lined up. I don't have a screen to look at, I'm just assuming it's lined up. Having the same n value. Now, an n value will relate to the level that you're working with. So, this first orbital here will have an n equals 1. The second one here will have an n equals 2. And these n values denote what shell the electrons are located in. And that's going to correlate to things within the periodic table and make it, as you get more familiar, it'll become easier and easier to pick out the pieces that you need to work with. And then, what we're going to later look at is what's called the subshell. So we have a shell, the outer part, then the subshell, the part that's sub, inside, underneath. A set of orbitals of the same type. A set of orbitals of the same type. Okay, I'm going to break this down a little bit strangely right now, and we're going to jump from there. So hopefully it's not too crazy of a jump. We will go back and discuss electrons, atoms, and how it's all filled in the shell shortly. I'm going to shift this camera over. There we go. I just want to stay in the center of the frame. That way when I even do some editing, I can remain there. Okay. It's all a position game. Okay, so first off, what am I going to draw? I'm going to draw a chart that shows increasing energy. As we go up, energy increases. And as you think of filling these shells, energy is going to increase as we move up along the shells. So all the way at the bottom, we have what's called the n equals 1 shell. This is the first orbital, the first thing surrounding the nucleus, where the first groups of electrons will go in n equals 1 shell. As we go up, you can probably guess what's next. N equals 2. From there, and these spacings will later on have a role, but they're not critical right now. N equals 3, N equals 4, so on. As we go up, we get higher energy levels. We're just going to focus on the first 4. And this is going to correlate also, the N levels also correlate to rows within the periodic table. So, first element, hydrogen. Atomic number 1. What do we know about hydrogen? Well, you go to your periodic table on the back of your textbook, I hope you all brought it home, I told you to, you see hydrogen. It has an atomic number of 1, symbol of H, name hydrogen, and an atomic mass. That's the average atomic mass. We'll review that again later. So it has a mass of 1. Mass comes from protons and neutrons. So in the middle, we'll have an atomic number of 1. We're only going to have 1 proton in the nucleus. If we're talking about a neutral atom, it's in that nucleus. Surrounding that nucleus, how many electrons can we have? A single electron. Okay. This would be the hydrogen atom, part of the construction across the road. Next to hydrogen is our helium atom. Helium atom is, I need to make a better copy of this, is number 2. It has a mass of 4. Okay, so what does that mean? Well, that means within the nucleus it has atomic number of 2, so that means 2 protons, which have both masses of 1. It has a mass of 4, so that means there's going to be 2 neutrons as well in that nucleus. So that's the nucleus. Now, surrounding the nucleus, it has an orbital of electrons. Now, remember, hydrogen and helium are in the first row. They have an orbital of electrons. And what we're going to go, and I'll go back to this. I know we haven't discussed this in its entirety, but electrons start individually, get to a certain point, and they begin to pair. And I will just explain that more. So, hydrogen, 1 electron. Helium has 2 electrons. These electrons are paired up in that orbital. And as we go on to doing Lewis dot diagram and discussing bonding, pairing is what the electrons are looking for. Okay, that's the first row. Can I fit any more electrons in that first orbital? No, it's a small orbital. It's a low energy. It's not going to have a lot. So what we end up having is we have the suborbital. The suborbital, the subshell, is going to be here. And it's going to be called the 1s subshell. Okay? 1s subshell. I am going to take another piece of paper and put date on number 1 on top of that so I know, and I'm going to come back to that. Just set that aside for right now. Okay. Now, we're going to look at elements in the second row of the periodic table now. We're going to look at elements over here, starting at lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. We're going to look at those and we're going to discuss the energy levels, shells, and subshells going on with them. So, straighten out my paper, and I'm going to go through and I'm going to draw a Lewis dot diagram of each one. Now, these are a step beyond the Bohr model. A Lewis dot diagram is where you begin filling the orbitals with electrons and then going back and pairing up after you individual. So, we've established 2 electrons in the first orbital. So n equals 1 can hold up to 2 electrons. All right, wonderful. And if you're interested in my voice and listening to me, I've been doing evening readings, which I imagine you've been seeing me share on the Google Classroom. I will continue to do those, and I'm going to put them on a different platform, and I have shared with you on the Google Classroom what that platform is. It's going to be another classroom. It's going to be just called Reading with Gappy. I've shared the class, so go ahead, like it, sign up. I'm putting them on my Learn68 YouTube channel. Okay. N equals 2. Okay, awesome. So, lithium. Atomic number 3. Average atomic mass, 6.9. We're going to take an atomic mass of 7. We're going to round that up. We're going to have an atomic mass of 7. Okay. Working with these whole numbers is going to make it easier when we're counting protons and neutrons. Okay. Atomic number, oops, forgot the R there. 3, that's equal to the number of protons. 7. The atomic mass is all the things in the nucleus that weigh something. So remember, relative, a proton weighs 1, a neutron weighs 1, and electron weighs 1,837th of a proton. So it's going to take a lot of those. So electrons don't contribute to a mass as far as we're concerned. But the protons plus neutrons add up to 7. So as long as you know the atomic number and as long as you know the mass, you can figure out how many neutrons are in an atom. Okay, those are two critical pieces of information to give when you're working at the atomic level. Okay, so if I have 3 protons and I have 7 protons plus neutrons, how many neutrons do I have? Well, it's just a basic algebraic expression. I'm going to work over here on the side now. Well, we have 7 is equal to P plus N, but I know P equals 3. I can put 3 in for P, simple substitution. So I want to isolate N. I subtract 3. 4 equals N. I have 4 neutrons. So in my nucleus, I have 3 protons and 4 neutrons. All right, let's draw my lithium nucleus. That's right, that's what I'm doing. Nucleus. Proton, 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 neutron, 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 neutron. Draw a beautiful circle around there. All right, I'm in row 2. Well, to get to row 2, I have to go through row 1. So that means to get to energy level 2, N equals 2, I have to also have been using N equals 1. Think about it. When you stack blocks, if you forget to put the bottom block on, all the other blocks just don't float on top of it. You have to have that bottom block to build that tower taller and taller. I'm doing lots of Legos, lots of buildings with my kids. Okay. How many electrons do we establish can go into the N equals 1 shell? A single electron. No, 2 electrons. 1, 2. Okay, when we're in chemistry, we're talking about a neutral atom. We're going to take a little sidebar here. Neutral. Neutral. What does neutral mean? Well, we talk about neutral. We have a similar word, neutron. Neutron has no charge. Neutral is when an atom has no charge. An atom with no positive or negative overall. So, protons and neutrons, or protons and electrons, cancel each other out. Every positive proton cancels a negative neutron. So, when you go through and count up protons, neutrons, and electrons, you have to see if protons and electrons balance out. If they don't balance, then it might have a charge, positive possibly, or a negative. So in this case, we are going to be working with a neutral atom, a neutral lithium atom. So if it's a neutral atom, and we have 3 protons, how many electrons will we have to have? Well, if we have 3 positives, and we have to have a 0 overall charge, we have to have 3 negatives. So, where am I going to write that? I'm just going to say electrons equals 3. Okay. How many electrons did I use to fill N equals 1 shell? 2. How many do I have left if I have 3 overall? Well, 1, 2, I need 1 more. So I'm going to have another electron right there. Awesome. Electrons, electrons. Okay. Let's look back at this table here. Well, I have the N equals 1 shell. I have an N equals 2 shell. Now an N equals 2 will have another subshell. It will have a subshell for 2s. So, the electrons in the N equals 1. There's 2 of them. There's going to be 1 2s electron. Now it's going to get slightly more confusing. I might just stick to... No, I'll do it this way. This will work better. Okay. Back to page 2. After lithium is beryllium. We're working with a neutral beryllium atom. B-E-R-Y. I never spell this one. L-L-I-U-M. I always want to put one L. Beryllium. It's neutral. Neutral means 0 charge. Okay. Atomic number 4. That tells us how many, what we have? Protons. When you look at your table, it has a mass of 9.01. We're just going to round it over to 9. Remember your rounding rule. If it's less than 5, keep it the same. If it's greater than 5, round up. So, 4, 9. That's protons plus N. Well, if I have 4 protons and a mass of 9, how many neutrons do I have? I'm going to have P equals 4, N equals 5. I'm not going to do that algebra. You're in Chemistry 11. If you don't know how to do that, contact me. I will help you work through these algebraic expressions. If it's a neutral atom and I have 4 positives, how many negatives will I have to have? 4 as well. Okay, let's go and fill our shells. So the nucleus. I am just going to do 4 P's, 5 N. Circle around the nucleus just to have it all nicely contained. And now we're going to do the N equals 1 shell. How many electrons can go in N equals 1? Only 2. Think about how many atoms are in the first row. Only 2. That's all we can put in the first row, in the first energy level, in the N equals 1 state. We can only put 2 electrons. 1, 2. Then we have more electrons because we have a total of 4 electrons. 4 electrons. We've used 2. How many do we have left? 2. All right, awesome. Filled that up. Let's take a look back. How many electrons can I fit at N equals 1? In the 1s orbital, the 1s subshell? I can fit 2 electrons. 1, 2. How many can fit in the N equals 2? 2 electrons in the 2s subshell. 1, 2. That's 4 electrons. That's what we are accounting for. It's looking good. We're going up step by step. Energy electrons have slightly different energies, and that accounts for some of the size and the shape. So if you look at the second column on the periodic table, so 1, 2. Let's focus this out and zoom. I don't know. Hopefully you can see this all. If not, look at the back of your textbook, back of your workbook. Hydrogen, helium, 2. That's the N equals 1, 1s subshell. Only 2 electrons fit in there. Second row, lithium, beryllium. 1, 2. They have filled the N equals 2, 2s subshell. Only 2 electrons fit there. 1, 2. Now we have 6. This is going to be slightly different. Let's take a look at that. Yes, we'll come back to filling in these all, but this will just begin to introduce it. Okay, let's zoom this back. Might be too high. Focus. Letting it focus. Let's take a look at boron. And we're going to begin to do this a little more quickly. Boron, atomic number 5. We're going to look at the mass, 10.81. Well, 0.81 is greater than 5. 5 or greater. We're going to round it up to 11. a mass equal to 11. So that means we have 5 protons. 5 taken away from 11 is 6 neutrons. It's an element with no charge. It has 5 electrons. Okay, let's start with our nucleus. Nucleus. 5p, 6n, giving us a mass of 11. And I know I'm going to have an n equals 1. I know I'm going to have an n equals 2. All right. As we go through and fill these electrons, it's going to get a little more confusing. But if you look at it in the sense of the subshell energy levels, it will always make sense. And then in the future, I will introduce a way to use it further. But just bear with me for now. So, 5 electrons. How many can I fit in n equals 1? Only 2. And I'm going to reiterate that 1, 2. How many do I have left over? 3. You begin by leaving them unpaired. 1, 2, 3. Okay. Awesome. Let's pop over to carbon, and I'll come back to the other table momentarily. Atomic number 6. Mass 12. So that means we have 6 protons, 6 neutrons. If it's a neutral atom and we have 6 positive charges, how many negative charges do we have to have? 6 as well. Okay. Carbon. I'm going to draw my line there. So we have our nucleus. I am now just going to continue to abbreviate. Instead of writing 6p, 6n, I'm just going to write C. It's a carbon atom. We've established up here what's in it. It's not always going to be the case, but you can, in cases, do that when that's been well established what it is. Okay. Orbital, that's n equals 1 shell. The n equals 2 shell. How many electrons go in the n equals 1 shell? The 1s can only take 2 electrons. How many do we have left over? We started with 6 and we've used 2. If you said 4, you're correct. 1, 2, 3. Now, there we go. We've started going around and we filled these 4 general areas. And this is how we're going to look at bonding. And it's going to be a little confusing, but it will begin to make sense as you continue on. So 6 electrons. Now let's take a step back before we get too far. 1, 2, 3, 4. I'm out of spaces. So what we're faced with is a different energy level, a different subshell. Within the n equals 2 shell, we have another energy level, and it's going to be called the 2p subshell. And within that p-type subshell, there are 3p orbitals. S has 1 s orbital. P has 3 orbitals. And we'll begin to discuss shapes and the general ideas later on. Okay. You can use the table like this, and as we go up, 2s, 1s, 2s, 2p, 3s, 3p. And as we go up, we begin to add more and more. The next energy level is actually, so let's look at the periodic table. Hydrogen, 1s. 2s, 2p. Each orbital can hold 2 electrons. So this is p orbital 1, p orbital 2, p orbital 3. 3s, 3p, 4s. Okay, 4s. Now it's really confusing. We get this middle block, this weird block. 10 elements long. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. S orbitals can't hold 10, p orbitals can't hold 10, so we're left with another thing. It's called d orbitals. And based on mathematical rules, the first time a d orbital can show up is at the n equals 3 energy level. So you think about it. Well, I started 1 at S. At 2, I got to have 2. At 3, I only have 2. Wait, that's not a pattern I'm looking at. But no, we actually will have what's called a d orbital. And it's going to be, as we go up, lowest energy, next, 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 then 4s. And then weirdly, just here, 1, 2, there's 10 elements. That's 10 electrons. That's 5 pairs. 1, 2, 3, 4, 5. The 3d orbital. Its energy is slightly higher than the 4s orbital. That's why it comes after the 4s in the periodic table. After the 3d, we then get the 4p. 1, 2, 3, 4p. And it continues on. N equals 5, we get 5s. 4d, 1, 2, 3, 4, 5. 5p. I messed it up. So, I need to stop and restart this other recording for a second. So, as you go through, we can place electrons in the orbital. So, hydrogen has available a 1s orbital. It only has this. So, a 1s orbital. I can put 1 electron. Now, when we draw orbitals and electrons, we do these little half arrows. So, this half arrow, half arrow up or half arrow down. This relates to counter spins that we will discuss possibly later, are electrons. So, 1s, there's 1 electron. How many electrons in helium? 2. 1, 2. Now, you don't have to always draw this. You can say that you have a 1s with 1 electron. Here you have a 1s with 2 electrons. You represent the number of electrons as a superscript next to the orbital and subshell you're working with. Let's look at the other sheet. Lithium. We have lithium. We have 1s with 2 electrons. So we'd say 1s, 2. And we have a 2p. I'm sorry, a 2s with 1 electron. 1s with 2, 2s, 1. Beryllium. Well, 1s, 2s, 1, 2, 1, 2. How many 2s's? 1, 2. As you go up, you fill the lowest energy levels first, so that's why we're not jumping right to the P. So, that 2 shouldn't be there yet. I got ahead of myself. So this would be a 1s2, 2s2 electron configuration. And if you go through and you look at some higher level chemistry books, and you look at some higher level chemistry periodic tables and notations for the elements, it will tell you how many electrons are filled in each subshell. So you're going to see these huge strings. You can identify an element based on 1s2, 2s2, 2p6, 3s2, 3p4. Which element would that be? Well, you can work your way through the table and figure that out. But let's first go through boron. We have, now I'm going to do these in increasing energy like I should be. We have a 1s, 2s, and this is where we begin to get into 2p orbitals. How many s electrons? Always 2. You can never have more than 2 s electrons. So we have a 1s2, 2s1, 2, 1, 2, 2s2. Now the next energy level as we're going up is the 2p or subshells, the p orbitals. We only have 1 electron to go there. So we have a 2p1. Carbon. Now again, we're starting in here at 1s, 2s, 2p. You're going to begin to notice a pattern. The shell, prior to the shell that the element is in, is always going to be full. Two in the 1s orbital, 2 in the 2s orbital. That leaves us with 2. That means we have 2 in the 2p. Now, Pauli's exclusion principle is you can't have paired electrons until you fill the electrons in the shell. I will define that later. I'll go over that later, but in the time, keep them individual as we fill them up. All right, so that gives us an arrangement of 1s2, 2s2, 2p2. Now, a future shorthand way, Okay. I hope you're beginning to see a trend here. So carbon is a 1s2, 2s2, 2p2. After carbon comes nitrogen. What do we hypothesize nitrogen is going to look like in an energy shell atomic orbital arrangement? Well, good question. Nitrogen atomic number 7, average atomic mass is 14.01. We're just going to work with a mass of 14. So that means I have 7 protons. Atomic number is always equal to protons. Don't forget that. Mass is protons plus neutrons. That means neutrons is 7. It is neutral, so we have 7 electrons. You can go through, you can fill that. If you notice for the beryllium, the lithium, boron, and carbon, we all had the 1s2. It's going to be the same. The inner orbitals are always going to be the same. We're going to focus on the outer energy level, the outer shell. So I'm not going to draw the inner shell anymore. I'm just going to put nitrogen. And this is the n equals 2. Okay. N equals 2. Well, how many electrons are the 1s? Always 2. So a shorthand way to figure out how many electrons you're going to be working with in that n equals 2 or n equals whichever number is counting over. There was 1 electron. There was 1 electron in lithium. 2 electrons in beryllium. 1, 2, 3 in boron. 4, 5. As you go over, you just count. That's how many electrons are going to be in the outer shell, and that's going to relate to the valence principle. So, nitrogen, I have 5 electrons in the outer shell. You're going to begin pairing them individually. I'm just going to do ease. 1, 2, 3, 4. After the 4th one, this is because there's only 4 possible orbitals in the n equals 2 state. There's a 1, 2s, 1, 2p, 2, 2p's, 3, 2p's, so giving us a total of 4. Those are filled, and then we begin pairing them up again. So, it has 5. Bam. And we talked about and established that there's already 1s electrons. And there's always going to be a 1s2. Which element has that configuration exactly of 1s2? Helium. 2s, 2p are what we're working with here. 1, 2, 3, 1. There's only one s-type orbital and 3 p-type orbitals. How many electrons do we have? We had 5. 1, 2, 3, 4, 5. 2s2, 2p3. So I could go through and I could say, well, nitrogen, it has a 1s2, 2s2, 2p3 electron atomic configuration. A shorthand way to say that is taking the full orbital and saying, hey, actually helium has a 1s2, and then 2s2, 2p3. But which one has a 1s2 and a 2s2? Beryllium. And how can I substitute that? Well, a helium electron configuration is 1s2. Why can I put beryllium? Because a beryllium configuration is 1s2, 2s2. As you get into higher orbital elements, higher energy level orbitals, it's going to be a lot of writing, because we end up introducing f orbitals after the d orbitals, and that is the lanthanide and actinide, the 14 groups here. Imagine having to write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and that all the way to 6f, or 7d, or sorry, 7p. It gets to be a lengthy process. So, what I would like you to work on is I want you to go through and I want you to write the electron configurations of the following. Fluorine, neon, and the electron configuration is just the 1s2, 2s2, 2p3. I don't want you to do any shorthands yet. I'm introducing it as a way we use it in the future, but I need you to get in habit of filling it. You can fill out the orbital diagram if you want. 3 is going to be sodium. I'm going to give you 10 in total, I know. We're going to do a silicone, a sulfur, argon. I want you to try your hand at titanium. Zinc. Bromine. And krypton. These are going to get trickier. They're going to get things. But if you look back at my first sheet, and remember, the energy levels, I will reference which page. Let me see where the atomic orbitals are in your text. Should look this up earlier. I can't find it. You can sit here and watch me while I do this for a minute. E71. Let's try that. So chapter 5 is where we had previously been working. And it begins to talk about it here. If you look at your text on pages, you can take a look through. I know we're not going to worry about quantum numbers, N, L, M sub L, but I want you to consider this table, table 5.4.1, and figure 5.4.4. This summarizes it nicely. And then figure 5.4.6 is essentially what we've been looking at right now. Increasing energy levels, telling you where they are being filled. So that's what you're going to use to complete numbers 1 through 10. You're going to essentially go through and fill as you get them. All right, if you have any questions, put a chat comment out, send me an email at richard.gaffney@learn68. I'll give you guys several days to work on this, so expect to hear from me as in class, in a full class context, and say next Wednesday or so, and then I hope to be able to give another assignment and another bit of work for you guys to work on Thursday. So you can go through and you can read about it. Here it does talk about the Pauli exclusion principle. But hopefully my notes and explanation in practice, which you can review at your leisure, are good. If you need any changes or edits made to the video, if you prefer just to see the notes, or if you want to just see me talking, have the note picture on the side, let me know. I can provide that hopefully. In the meantime, I'm going to sign off and edit all these videos and get them posted. Have a wonderful day and enjoy your weekend.